All right, guys, this is section 3.5 of Trig, operations on functions. The first half of this is going to be really pretty easy. The second half has kind of a little bit of a trick to it. Homework for this section is right up here at the top of the page. It's also posted on a Google Classroom. So, example 1. They're just having you do sum and difference, which means adding and subtracting. Basically, you have two different functions, f and g. They might be called something else like h and k or whatever. And they want you to write the rule for f plus g and f minus g. Okay, so f plus g of x, which is written like this. Basically, you're doing the square root of 9 minus x squared plus the square root of x minus 2. Okay, like that. Now, because this is a square root, there's no way I can put anything together. If I was multiplying, I can maybe get rid of those square roots, but can't do anything to combine any of those, combine any like terms. I can't put them under one roof. So this is technically done. There's nothing I can do for that. And it just so happens that the same thing occurs when I do f minus g. There's really nothing I can put together either. I have just the square root of 9 minus x squared minus the square root of x minus 2. There's nothing I can put together. If there is, you combine like terms, but if not, you just leave it. So the next part is they want you to write the domain, and basically the domain is like what x can and cannot be. So looking at those two, f plus g and f minus g, I've got this thing going on right here, and we have to decide what x can and cannot be. All right. The two domain errors, again, as review, are a negative inside of a square root, and we don't want to ever divide by 0. So those are the two things that we're really looking for. Mainly here we are looking for negatives inside square roots because we don't have any division. We don't have any fractions at all in here. So that's mainly what we're going to be looking for. F plus g and f minus g. When you're looking at those domains, it might help to look at f and g individually, like what the domain of f and g are. So if f is the square root of 9 minus x squared, to figure out what the domain is, we know we can't have it be negative. 9 minus x squared cannot be negative. So basically we take 9 minus x squared and we set that equal to 0, which means that 9 equals x squared if we add the x squared over. And x is equal to positive and negative 3 if I take the square root. Okay, so looking at that on a number line, we have negative 3 and we have positive 3. And looking at numbers that I can plug into that equation, let's do like negative 4. Okay, negative 4 squared is 16, and 9 minus 16 is going to give me a negative number. Now that same thing is going to happen if I do positive 4. 9 minus positive 4 squared is going to be 9 minus 16, which is negative. If I test, like, let's say 0, 9 minus 0 squared is okay. So I can have any numbers between negative 3 and 3. So we'll write the domain of f as, oh, we can have that. Okay, negative 3, comma 3, we'll write it in interval notation. Okay, I do brackets around the negative 3 and 3 because you can include 3 and you can include negative 3. It would just give you 0 inside that square root. And then g, if we're doing g, x minus 2, we set that equal to 0, so x equals 2, and then we put that in a number line. And we say 2 is here. Let's test 0. 0 minus 2, I cannot have the square root of negative 2, so that's not going to work. But if I have a number like 3, 3 minus 2, I can do that. So 2 is inclusive, and it goes from 2 to infinity. Okay. So when you're doing like f plus g and f minus g, you're kind of looking at those two things happening at the same time, like these two equations happening at the same time. So what I have going on for one of the functions is I have a solid dot on negative 3 and a solid dot on positive 3, and it's connected in between them. And then I have 2 right here and a solid dot on 2, and it's going that direction. So basically a number like 1 or 0 would work for this equation, but it won't work for this one. So since it doesn't work for both pieces, and really f plus g and f minus g combines both of those together, I can't have this section right here. And like the number 4 would work for this equation, but wouldn't work for this one. So I can't have this one. So basically those two things are overlapping between 2 and 3. So the domain of f plus g and f minus g is just going to be between 2 and 3, like this. Okay, that's all that that's going to be. Holy cow. The domain is the ugly part. The rule is actually pretty easy because you just rewrite it and combine like terms. So there is that. All right. A, write the rule for this means multiply, this means divide. So multiply, divide, we're multiplying the square root of 3x times the square root of x squared minus 1. Now, since we are multiplying, we can combine those things. Since we're multiplying, we can put those things together. So we have it all underneath of 1 square root, and we've got 3x times x squared minus 1 is basically what we have going on here. Okay, and then let's see, we can distribute. Let's see, I'm looking at the book right here. Let's see if they distribute or if they just leave it. Hold on just a second. No, they went ahead and distributed. Yuck, yuck. Okay, so they did the square root of 3x to the third power minus 3x. They distributed that 3x through. So this is what f times g of x is, and then we want to do f divided by g of x. So we want to do, oh geez, the square root of 3x over the square root of x squared minus 1, and that is going to be one big giant square root, like that. Okay. So this is the division. Now we need to find the domain of f times g and f divided by g. Okay. So looking at f and g individually, 3x, if we set that equal to 0, and divide by 3, x equals 0 still. And on a number line, if we have 0 here, if I have a number less than 0, like -1, and where are we at here? If I have a number like -1, and I plug it into that equation, 3 times -1 is going to give me a negative, so I cannot have that. If I plug in a positive 1, I can take the square root of 3, so that will work. So f, oh my gosh, we have such a mess here. All x's that are greater than or equal to, let's say, 0. So we'll write it like this. 0 to infinity will work for f's. Okay. For g's, x squared minus 1, I'm going to set x squared minus 1 equal to 0. And that means x squared equals 1, and x equals plus and minus 1. If you take the square root of both of those. The square root of 1 is 1. So, I'm sorry, I am all over the place. -1, positive 1. If I plug in numbers that are less than 1, like -2, if I take 2 and square it, -2 and square it, that's 4, and 4 minus 1 is good. So I can have this part. If I have a number like 0, 0 squared minus 1 won't work. And if I have a number like 2, 2 squared is 4, 4 minus 1 will work. So, let's see. G will be the ranges from -infinity to -1, including -1, and including 1 to infinity. It will look like that. Okay. So we have that going on there. If these two things are combined with one another, we're only looking at numbers that we can plug in between 0 and infinity, and we're only looking at, and this is basically a wider range than that. So numbers between 0 and infinity don't include those. It kind of like knocks that out. If you need to see that on a number line, this one is like -1 that way, and this one is +1 that way, and 0 is 0 that way. Okay, so numbers that are over here will work for this bottom part, but won't work for the 0 part. Okay, numbers that are inside here, like 1/2, will work for this part, but not for this part. So our restriction is just from 1 to infinity. Okay, that's what our domain of f times g and f divided by g is. Okay, is just from 1 to infinity because it's the least restrictive domain. Okay, now in addition to that, there's one more little teeny tiny thing. When you do division, right here, I end up with a square root, or I end up with a denominator basically. So in addition to this, not only can we only have numbers that are from 1 to infinity, we can't have this thing right here be 0. And what will make this thing 0 is if we plug 1 in. So 1 squared minus 1 will end up being 0, and we can have that inside of a square root, but we can't have that in a denominator. So now this changes from this to a bracket because we cannot have 1 exactly. So my domain of f times g can stay as 1 comma infinity, but f divided by g is parentheses 1 comma infinity because we can't have that 1 in the bottom there. Okay, that is such a mess. Look at all that crap. Yuck. It gets better. This is easier. Okay, now A, B, C, D. These are the easy ones. So we have an F and we have a G, and oh boy. Okay. G composed of F of 2. This a lot of times is written like this instead. Okay, and basically that means plug 2 into the inside function, which is f, and then plug that number into g. So we basically want to find f of 2. So that means plug 2 into this equation. Okay, 4 times 2 squared plus 1. 2 squared is 4, 4 times 4 is 16, 16 plus 1 is 17. So f of 2 is 17, equals 17. Now if f of 2 is 17, then 17 is basically taking the place of f of 2, and so g of 17 is what we need to find next. G of 17 is 1 over 17 plus 2, which is 1 over 19, and that is the final answer. Okay, so you plug it into the inside, and then you plug it into the outside, and then you're done. Okay, same thing with this one. This one they want us to plug into g first. We're plugging -1 in there, so 1 over -1 plus 2 is 1 over 1, which is just 1. That's exciting. Then we need to find f of 1. We plug it into the outside function. So 4 times 1 squared plus 1 is 5. And that's my final answer. So those ones are a little nicer. Just remember to plug into the inside first and then the outside. Okay. Now, what does it look like if you have g composed of f of x and you don't have a number in there? Okay. So again, you'll see this written like this sometimes. This basically just means take f and plug it into the equation of g. So this guy right here for f is being plugged in where the x is in the g equation. So instead of g being 1 over x plus 2, now that x is being replaced with 4x squared plus 1. Okay, f is going inside of g. And then we can do one more just little simplification here. 1 over 4x squared. That 1 and that 2 can go together to make 3, and then that's all you have. Okay. We're not going to find domain and range domain for that. Right? This one over here is just doing them in the reverse order. So g is going inside of f. So I'm doing this guy is going into there. Okay. And so that instead is 4x squared plus 1. 4x squared plus 1. And in that x squared is that. Okay. And let's see, I'm going to do just one more little simplification thing for that. This 2 can basically do this. I can square the 1 and I can square the quantity on the bottom. 1 squared is just 1, and I'm going to multiply that by 4. So 4 over x plus 2 squared plus 1, like that. I'm just going to leave it like that. That makes it a little bit nicer. Okay. If you left it like this, I'm not going to count it wrong. That's totally fine too. So there is that. Okay. They talk a little bit about the domain of G composed of F, and it basically just says start with G, start with F, find their domains, and then see if there's any extra things that you need to restrict domain from, kind of like we did with the denominator. Okay. So let's go to the back side. Find the domain of the composite function. Okay. So G composed of F, and then F composed of G. And I'm not going to do all, well, maybe I'll do all the parts of the domain. We'll see. We'll see. G composed of F. So that means we are taking F as our inside function. So we're taking this guy and we're substituting him into there. All right. So instead of it being x squared minus 5, we put the square root of x in there. All right. Focus. Focus, focus. There we go. Okay. Now, the square root and the square are going to cancel each other out, so basically we have x minus 5, and that's what g composed of f looks like. G composed of f. Okay. Then let's do f composed of g. So f composed of g means I'm taking this guy and I'm plugging him in there because g is on the inside now, right? If I take that and I substitute him in there, now I can no longer, that square and that square root don't cross out anymore because it's trapped by the minus sign. So this is basically all that I can do for f composed of g. Now, let's look at the composite function, okay? So, this function right here is a linear function, x minus 5. There is nothing that I'm restricted by, nothing that I cannot plug in for x. But since this guy was made from two other functions, I really have to look at f and g individually. So even though this guy's domain is basically all reals, I have to look at f and g individually first, and that's going to restrict my domain. All right? So f, this number right here, or this guy right here, the square root of x, numbers that I can and cannot plug in for that, I can't have any negatives. So basically, 0 to infinity is my domain for f. G, there's no square roots, there's no division by 0, so g is all reals. Okay? So now, instead of this guy being all reals, the domain of g composed of f is restricted. Here I have all reals, and 0 to infinity. 0 to infinity is my domain. Okay? F composed of G is the same way. F composed of G is the same way. I have these two things going on, and then we look at this guy individually. Oh boy. So x squared minus 5, I set that equal to 0. X squared equals 5, and we take the square root. Oh shoot, my lights just turned off. All right, so we have plus and minus the square root of 5. Negative square root of 5, positive square root of 5. I'm just going to test like 0 in between there. If I plug 0 in, 0 squared minus 5 is going to give me negative. So I can't have that. So I have this and beyond, and I have this and beyond. Okay. Now we need to look at the most restrictive. So I have negative infinity to negative 5 as one of my parts, and then from, square root of 5. Negative square root of 5 to infinity as my other part, okay? And so which of these three, this one, and this one, give me the most restrictive, like, domain here? Okay, negative square root of 5, positive square root of 5, 0. This top one is going from here that way, this one is going from here that way, and this one is going from here that way. So these two pieces are this one, and then this one here is this one. So anything that's underneath of here works for this equation, but not for this one. Okay? Anything that's between 0 and the square root of 5 works for this one, but not for this one. So really, we're only looking at this side here because that's the only piece that works for both. So for f composed of g, it goes from the square root of 5 to infinity like that. Okay? And here are your domains. All right? Yuck, yuck, yuck. I hope I don't give you too many of those. All right. All right. These ones are easier. The square root of x, or the square root of 3x squared plus 1, they want us to write that function, which is called h, as a composition of two functions, okay? So basically we're like breaking this thing down and we're seeing like what pieces are involved in there. So let's call like f of x, I see a square root in there, so let's just say the square root of x, okay? And let's do g of x as like the part that's on the inside, 3x squared plus 1. We can write h of x as f composed of g of x. It's basically like g of x shoved inside of f of x. And this is how we can write that. So this guy, with these two functions defined that way, is a way of writing this function in pieces, basically. Okay? All right. I'm going to skip this problem because it's kind of similar to what we've been doing already. So absolute value square root, we're not going to worry about that too much. Example 7, though. This is a circular puddle of liquid is evaporating and slowly shrinking in size. After t minutes, the radius of the surface of the puddle measures this equation. Okay, the area of the puddle is given by this. All right, so this is an application of when you compose one function inside of the other. So like this guy is what the radius is equal to in terms of time, because time is my variable here. So basically we want to take this equation and we want to embed that inside and substitute that for r. So instead of being pi radius squared, we're plugging 18 over 2t plus 3 in for the radius. Okay. And so this is basically like kind of finding the area in terms of time and kind of bypassing the radius. Rather than me having to plug 12 in to find the radius here and then plugging it in here to find the area, I just kind of do that all in one shot. Okay? If I'm able to plug 12 in for t into this equation, I then will be able to find the area. So I have pi 18 over 2 times 12 is 24, plus 3 is 27 squared. Let me find a calculator. If I'm ever moving too fast in this video, feel free to rewind or go back or whatever. Okay, so I'm going to do, I always like to do the stuff in parentheses first. So parentheses 18 divided by 27 squared, and then times pi button's there. There we go. Enter. So the area is 1.396, and that is in inches squared. So it's basically like finding, it's bypassing the radius and going straight from area to time. Now, one of the other examples that I use, or one of the other applications of composite functions, is like when you go into a store. It drives me crazy that when you go into a store, there are some customers out there that think that if I go in and there is an item that's on sale for 50% off, and I have a coupon for another 50% off, some people think it's free. It's not free, okay? Basically, it's the first function, the sale, is 0.5 times whatever that value is. And the second coupon, or the coupon, is another 50% off times x. So you're basically embedding this coupon inside of the sale price already, which makes it look like 0.5 times 0.5x, which is 0.25x. This is the amount of money that you will end up paying at the end. You'll end up paying 25% of what the item was already. It's not going to be free. Okay, so this is another application of composite functions. It drives me crazy when people don't understand how that works. So there you go.